Good morning, students. Chapter 5, Magnetism and Matter. Yes, in the last lecture we have discussed about behavior of magnetic dipole in uniform magnetic field. And yes, we got some similar result that we have obtained in chapter number 1 in electrostatics. So now in this lecture we will compare the electrostatic analog. Means what is analogous between electrostatics and magnetism. First of all, we will see electrostatics. Yes, in electrostatics, first quantity that we know that if I am considering one dipole, with the help of one dipole, we will understand this. Okay, see, here it is. If it is dipole, electric dipole, negative Q charge plus Q charge. Distance between them is 2a. Okay, electric dipole moment is from negative charge to positive charge. And dipole moment, what is dipole moment? Dipole moment P is equal to, it is Q into 2a. And its direction is from negative towards positive. Yes or no? Yes, you know this already. Okay, then on axis of dipole, what is equation of electric field? E axis on axis of dipole, what is electric field? We have obtained 1 upon 4 by epsilon 0. It is 2p upon rq. 2p upon rq. Yes or no? Yes, you know it. EA is equal to, it is 1 upon 4 by epsilon 0, 2p upon rq for short dipole. Yes, for short dipole. We have obtained this equation. Also, electric field on equator. It is minus 1 upon 4 by epsilon 0 p upon rq. Yes, on axis, electric field is in direction of electric dipole moment. On equator, electric field is in direction of opposite electric dipole. Yes or no? Yes, you know this each and every point. Also, torque on dipole in uniform electric field. That is, torque tau is equal to, it is P cross E. Clear about this? And what is potential energy? Again in uniform electric field. So yes, the potential energy U is equal to, it is minus P dot E. Yes, you know each and every topic. Also here, fundamental or electric dipole, it has two charges. So yes, charge Q. What is charge Q? What is constant in each and every equation? 1 upon 4 by epsilon 0, 1 upon 4 by epsilon 0. So yes, here constant we have. It is 1 upon 4 by epsilon 0. We have constant 1 upon 4 by epsilon 0. Clear? Dipole moment. Yes, I will write word electric dipole. Clear about this? So yes, in electrostatics, you know this each and every topic. Okay, under electrostatics, what is fundamental? It is charge. What is constant? 1 upon 4 by epsilon 0. Electric dipole, minus Q plus Q charge. Dipole moment, distance 2a. Dipole moment, electric field on axis, electric field on equator, torque and potential energy. Yes, you know each and every equation. Also, yes, if I want to write force, how to write force? Okay, force F is equal to, it is Q into E. It is Q into E. So in magnetism, how to write this each and everything? In magnetism, yes. Now we will write the same things in magnetism. So first of all, in electrostatics, fundamental is charge. So in magnetism, it is pole strength. We have to compare this charge with pole strength. We have to compare this charge with pole strength. We have to compare with pole strength denoted by P. In electrostatics, constant use is 1 upon 4 pi epsilon 0. Here we have to use constant mu 0 upon 4 pi. Mu 0 upon 4 pi. Clear about this? Mu 0 upon 4 pi. Any doubt? Now, here it is electric dipole. Now here I will draw magnetic dipole. Here I will draw magnetic dipole. Magnetic dipole means nothing but magnet. Magnetic dipole means nothing but magnet. It is north pole, it is south pole. Clear about this? Okay, so yes, this north pole and south pole, they have some pole strength. They have some pole strength. They have some pole strength. And yes, distance between these two poles is 2L. So yes, if you can compare minus Q plus Q, north pole, south pole. Distance between them 2A, distance between them 2L. Now next is magnetic dipole moment. Magnetic dipole moment. Magnetic dipole moment. Magnetic dipole moment, that is M is equal to, if you compare students, see, charge you have to compare with pole strength. So yes, it is P into 12. It is P into 12. So yes, electric dipole moment P is equal to Q into 2A. Here magnetic dipole moment M is equal to this P into 12, where P is pole strength. Also, direction of magnetic moment inside magnet, it is from south to north. It is from south to north. It is direction of magnetic moment. Okay. So yes, it is from south to north. Clear about this? Clear about this? Now, it is called axis of magnet. Okay, and it is called equator of magnet. It is called equator of magnet. So yes, it is axis of magnet. So on axis of magnet, yes, in theory of this chapter, we have obtained one result on axis of dipole or for short magnet. For short magnet. For short magnet. For short magnet. We know that electric field, magnetic field on axis BA is equal to, it is mu 0 upon 4 pi 2m upon r2. 2m upon r2. Yes, this result we have obtained in previous lecture. BA, electric field on magnetic field on axis is equal to mu 0 upon 4 pi 2m upon r2. Now see, if you compare here, if you compare EA 1 upon 4 pi epsilon 0, so it is replaced by mu 0 upon 4 pi. 2B, so here it is 2m. R2, here it is R2. You see, it is called analogous between electrostatics and magnetism. Similarly, yes, we have obtained this equation. Now for equator, we will not obtain equation, but we will write directly with the help of this analogous. Okay, magnetic field on axis BE is equal to minus mu 0 upon 4 pi m upon r3. M upon r3 minus, it is in opposite direction of magnetic moment. It is in opposite direction of magnetic moment. Clear about this? Yes, and yes, in last lecture we have proved torque acting on magnetic dipole. Torque acting on magnetic dipole. Magnetic dipole in uniform magnetic field. In uniform magnetic field. In uniform magnetic field. Tau is equal to, here it is M cross B. Here it is M cross B. So yes, in case of electrostatics, you have to consider electric dipole moment P. Here you have to consider magnetic dipole moment M. Here electric field is E. Here you have to take magnetic field B. Magnetic field B. So do you understand what is comparison between these two concepts? Okay. Next question is, see, what was last question? Potential energy of dipole in uniform electric field. Here potential energy. Here potential energy of magnetic dipole. Magnetic dipole in uniform magnetic field. In uniform magnetic is minus m dot b. It is minus m dot b, and it is analogous to u is equal to minus p dot e. Clear about this? So yes, it is one analogous between electrostatics and magnetism. Yes, charge q, pole strength p, constant 1 upon 4 pi epsilon 0, constant mu 0 upon 4 pi. Yes or no? Force F is equal to QE. So here I can write force. Here I can write force. F is equal to P into B. Okay, P means pole strength and B means magnetic field. Here P is pole strength. Here P is pole strength. Clear about this? So yes, it is analogous between these two. Yes, here electric dipole moment P. So here we have to this magnetic dipole moment M. So yes, we have to, if I want to write analogous, then P is analogous to M. P means electric dipole moment. P means electric dipole moment. And M means magnetic dipole moment. And M means magnetic dipole moment. So see, electrostatics and magnetism, you can easily compare equations of these two different phenomena. Clear about this? What about electrostatics and what about magnetism? So if you know each and every equations of electrostatics, you can easily form equations for magnetism. Now we will see some questions. See, example 5.1. Magnetic moment M is equal to 6.7 into 10 raised to minus 2 ampere meter square. One magnet having magnetic moment this and moment of inertia I is equal to 7.5 into 10 raised to minus 6 kg meter square is placed in magnetic field which performs 10 oscillations in 6.70 seconds. Then you have to find what is magnetic field. Okay. Yes, we know one equation. What is equation? We have to find magnetic field. Magnetic moment is given. Moment of inertia is given. 10 oscillations in 6.70 seconds. So yes, you know equation. For 10 oscillations, for oscillations 10, time is 6.70 seconds. So for one oscillation, what is time? And that time is called time period T. T is equal to it is 6.70 divided by 10. So it is 0.670 seconds. Clear about this? Okay. Now you have to find what is magnetic field. What is the relation between magnetic moment, moment of inertia, magnetic field, and T? Yes, you know one equation. T is equal to 2 pi under root I upon M. T is equal to 2 pi under root I upon MB. Yes, you know this equation. So yes, you have to just put value 2 pi I and MB. See, you have to find T. So we will make subject. First of all, we will take square on both sides. So T square is equal to 4 pi square I upon MB. Yes, what we have to find? We have to find B to make it subject. So B is equal to 4 pi square I upon M T square. Clear about this? 4, you know what is value of pi, you know what is value of I moment of inertia, M is given, T is also given, so you can easily find what is answer. Okay, next is example 5.2. See what is example 5.2. Example 5.2, here it is. One bar magnet is placed in magnetic field such that axis of magnet makes angle 30 degrees with magnetic field. So yes, theta is equal to 30. Theta is equal, because here is, yes, if it is south pole, it is north pole. It is direction of magnetic moment. So yes, angle between them is theta is equal to 30. Magnetic field is given 800 Gauss. So it is 800 into 10 raised to minus 4 Tesla. And in this situation, torque acting on magnet is given, that is 0.016 Newton meter. So what is first question? First question is you have to find magnetic moment of magnet. Yes, you can use this equation. Torque tau is equal to, it is mb sin theta. So what is value of m? M is equal to, it is tau upon, m is equal to, it is tau upon b sin theta. Yes, you are given value of tau, you are given value of b, and yes, you know what is value of theta, so you can easily find. Clear about this? What is question B? What is work done in moving from most stable to most unstable position? Most stable position means magnet aligns in the direction of magnetic field. Magnetic moment is in direction of magnetic field. So theta 1 is equal to, here it is 0. Most unstable condition means it means what is angle? Yes, angle between them. Theta 2 is equal to, it is 180 degree. We have to find what is equation of work done. Yes, in last lecture we have obtained equation of work done, that is W is equal to, or you know that delta U means it is U2 minus U1, means it is U2 means in final position. See, magnet is same, magnetic field is same, just angle changes. So yes, here it is minus mb cos theta 2 minus mb cos theta 1. Clear about this? So yes, you can write this as minus mb cos theta 2 plus mb cos theta 1. So if you take out mb as common, then mb common, then it is yes cos theta 1 minus cos theta 2. You know what is value of m from equation number 1. You know what is value of p, 800 into 10 raised to minus 4. Cos theta 1 means cos 0, it is 1. Cos 180, it is minus 1. So yes, what you will get here is mb cos theta, yes it is 1. Cos theta 2 minus, it is minus 1. Minus will become plus. So yes, here it is 2mb. Here it is 2mb. You know what is value of m? You know what is value of p. You can easily find with the help of this data. Now what is question C? See, a bar magnet, this bar magnet, okay, this bar magnet which is given, is replaced by a solenoid having cross-sectional area A 2 into 10 raised to minus 4 meter square, numbers of turn 1000, and having same magnetic moment, means magnetic moment you have to write, which is obtained in equation number A. So you have to find what is current flowing from solenoid. We know that for solenoid, magnetic moment, how to write magnetic moment? Its equation is M is equal to NIA. Magnetic moment M is equal to NIA, where N numbers of turns, I current, and A is area. So yes, you have to find I. So I is equal to, it is M upon NA. I is equal to, it is M upon NA. M, magnetic moment which you have obtained in equation number A, and A, they are given. Clear about this? So yes, with the help of this equation, you can easily find what is current flowing from solenoid. Clear about this? Okay. Now, see, yes, question is over. We will solve one more extra question. If you are given two magnets like this, placed like this, two identical magnets having magnetic moment same. Then if two magnets are placed like this, then you have to find what is resultant magnetic moment. Find resultant magnetic moment. Find resultant magnetic moment. Resultant magnetic moment. How to find? See, these two magnets are identical. Yes or no? Yes. So, first of all, we will see direction. Magnetic moment of this direction, in this direction. For this magnet, it is in this direction. Yes or no? It is direction of M1. It is direction of M2. And we know that M1 and M2, their value is same. So I can say it is M. I can say it is M. Clear about this? Two magnets, they are identical. So their magnetic moments are equal. M1 is equal to M2 is equal to M. But magnetic moment is vector quantity. Its direction is from S to N, S to N. So what is equivalent magnetic moment? How to write? See, resultant magnetic moment. Resultant magnetic moment. How to write? M dash is equal to M1 plus M2. Yes, it is vector quantity, so we have to write like this. We have to write like this. M1, M2. Yes or no? Now how to find its magnitude? How to find its magnitude? According to law of parallelogram. According to law of parallelogram. Yes. How to find its magnitude? M dash is equal to, here it is, under root M1 square plus M2 square plus 2M1 M2 cos, what is angle between them? Yes, here it is 90. What is angle between them? M1 and M2? Yes, it is 90. So here M dash is equal to, it is under M square plus M square plus M square plus M square, it is 2M square. So what is value of M dash? It is root 2M. It is root 2M. So it is one extra question. Okay, how to find resultant magnetic moment? It is one extra question. Okay, how to find resultant magnetic moment when two magnets are arranged like this? When two magnets are arranged like this. Clear about this? Clear about this? Now I will draw two figures. I will draw two figures, and you have to find resultant magnetic moment. You have to find resultant magnetic moment. See, figure number 1. Figure number 1. If two magnets are placed like this, it is N, it is N. Here it is S and here it is N. This angle is 60 degrees. So yes, these two are identical. These two magnets are identical. You have to find what is resultant magnetic moment. In second case, it is N, it is N, it is S, and it is N, and this angle is 60. Clear about this? So yes, in these two cases, you have to find what is equivalent magnetic moment like this. Yes, you will have to use law of parallelogram, but identify direction and solve these two questions. Clear about this? Yes, students, write down from board, make notes, send notes. If you have any doubts, then yes, try to solve your doubts instantly. Plus, do like, share and comment our video.